And ladies and gentlemen, I think it is time to start. My name is Chris Stewart. Welcome to the Syzygy podcast. This is very exciting. Emily Brunsden, my podcast co-host, just joined me here on the Zoom. She's on the other side of the Zoom. She's on the other side of the country. Emily, hi.
Hello, hello.
This is very exciting. We've done live shows before, but I don't think we've ever done a live broadcast show before. Have I got that right?
That's probably right, yeah. You're not going to be able to edit out all the weird things that I say.
I'm not. Actually, that's not strictly true. We did do a live broadcast to the stars. We actually broadcast an episode of the podcast to, what was the star? It's Beetlejuice.
Beetlejuice.
Yeah, a number of episodes ago. Anyway, that's a story for another time. Welcome to the Syzygy podcast. For those of you who have listened before, you know what this is about. This is an astronomy podcast in which I, a non-astronomer, talk to Emily Brunsden, Dr. Emily Brunsden from the University of York Department of Physics, who is an astronomer and knows about this stuff, about all the fabulous things that happen in the universe. And tonight is a very, very exciting night because we're live. We're talking about a really, really interesting topic. And for the first time in like forever, we have a couple of very special guests who are going to join us a little bit later on in the show. We're going to be talking tonight about one of the most fascinating topics in all of astronomy, in a field which is full of fascinating topics. We're going to be talking about one of the really big ones. We're talking about dark matter, this mysterious stuff that makes up, what is it, something like 80%, only 80% of the entire universe. So we'll be talking about that. But before we do, a couple of technical points. First of all, this is going out live as part of the York Festival of Ideas. We've done live shows at the York Festival before. Normally they've been in front of an audience rather than having you all hidden there behind your Zoom app at home. And I'm just watching the numbers ticking over down below. We're up in somewhere approaching about 10,000 people watching this broadcast right now. Part of York Festival Ideas has gone completely online this year for the obvious reasons. And it's been going for the last couple of weeks. We've had more than 60 events across those 2 weeks. So there's still another weekend to go. So if you're interested, stick around to the end and we'll give you the information on how you can find out other stuff about the York Festival of Ideas. So thank you very much for joining us on this one tonight. If you do happen to have a bit of a Wi-Fi glitch, you're kicked out, you can always rejoin the Zoom using the link that you got with your invitation. So you can just come back and join us if you get kicked out, or if you need to duck out and make a cup of tea or go to the loo or something, you can come back in. That's all totally fine. And we're having a special question and answer session at the end of this show. Down the bottom of the Zoom screen, you should be able to see a Q&A button, and a bunch of people have already got in there. Someone even got in before we'd even started. Before we'd even started the episode, someone was in with a question about dark matter. So if you want to ask a question, we may not be able to get through all of them, but we will do our best to get through as many as we can. I'll be managing those as we get to question and answer, and sending them out to Emily and to our special guests for this evening. So that's how that's going to work. Emily, we're talking about dark matter tonight. Now, correct me if I'm wrong, but dark matter is an ever so slightly embarrassing problem for astronomy. Is that right? Have I got that right? It's not a little thing.
Absolutely.
This is a big thing, right? What's going on?
Absolutely. You ask an astronomer, what's the universe made of? It's made of stuff, right? It's stuff out there. If you talk about matter, then you say, well, there's lots of matter out there in the universe. But it turns out that we actually have no idea what 85% of that matter is.
Okay, now hang on. That's
embarrassing.
That's not right. Okay, you people, you astronomers, you've got some of the best instrumentation ever. Like you've got telescopes in space, Emily. How can you not know what 85% of the stuff is? That's your job, surely. You had one job, to know what this stuff is.
Well, it gets worse than that because it's only been in the last kind of 50 years that we've even thought actually known, is it even there? We didn't know it was there for most of modern history.
All right, we should probably back up a little bit then. So, it's easy to be facetious about this incredibly embarrassing problem for astronomers, but let's dig down into it a little bit. There's matter. Yeah, when we talk about matter, we talk about that's the stuff that that me and the Earth and this computer and everyone listening at home, it's the stuff that you're made of. It's the atoms and the particles, and it also includes the photons of light and so on. It's the stuff of the universe, and that's what we see. That's what we measure when we look up into the night sky, right? Like whenever you're making observations about stuff. Yeah.
Yeah. So whilst we're observing things like stars and galaxies and planets, all those objects are made up of atoms, which have protons and neutrons and electrons and, the stuff that we understand, because it's the same stuff as what we have here on Earth.
Okay, so where's the problem then? Clearly, if we are missing some ludicrous proportion of the stuff in the universe, we must have stumbled over that at some point. So tell us about dark matter. When did we discover that there was a problem?
Well, we started doing some sums. I mean, astrophysicists love doing a few sums. And we were looking at particularly galaxies to begin with. So we were looking at how galaxies rotate. So you might have seen some beautiful pictures of things, big spiral galaxies that spin around. And whilst they spin kind of slowly in terms of our sort of time, our lifetimes, actually there's a lot of matter in a galaxy. So it tends to spin pretty quickly. And if you do kind of a bit of a sum and you say, well, okay, what's in a galaxy? You've got stars, you've got these planets, you've got gas, you've got dust, you've got all black holes, everything. You did a sum and you added up all the mass that you've got in a galaxy. It turns out that you fall a long way short of being able to explain how fast that galaxy is spinning. And that's a big problem because...
That is a problem because you really thought you understood what was going on, right? You just add up all the bits and you put it into the equations that we've known like forever and it should just work, but it really doesn't.
Yeah, and the consequence is that if you don't have some other matter there, turns out all your galaxies are going to spin and fly apart.
Which clearly they're not doing, so... Ergo, the matter must be there. So when are we talking about? When was this discovery made?
So we started doing rotation curves after we sort of got into radio astronomy, which was kind of looking at light, but not looking at light that we can see, looking at radio waves, which radio wave technology developed during the wars. And then after that, astronomers started repurposing it. Right.
So we're talking sort of the golden age of radio astronomy, what, in the 1950s, 1960s?
Yeah, 50s, 60s, we started measuring these galaxies. Yeah.
So you're looking at all this data coming from galaxy rotations and so on, and you realize that there's a serious problem in that we can't see a lot of the stuff that has to be there, and we know it has to be there because we can see how the galaxy is rotating. So what do you do as an astronomer at that point? What's your solution?
So I guess you then start to make a list of things. Let's say, okay, we've got some mass. We know some things about it. We know that it doesn't interact with photons because if it produced light, for example, or if it interacted with photons in any other strong kind of way, then we would see it.
You'd see it, right? That's the whole point. That's what you do, as previously stated.
So the dark is kind of a good astronomical description of it. It's dark because... for the most part, doesn't interact with photons. It's not entirely true because one of the other ways we do see where dark matter is actually by looking at how photons bend as they travel through space.
Right. Okay. Well, let's come back to that one.
For the large part.
So what you're saying is the dark in dark matter is most of everything else that we see because of the interaction between light of some form, whether there's visible light or radio waves or X-rays or something. The interaction between photons and matter, we see that interaction in some form. And you're saying that in most ways, at least, whatever this stuff is, it's not doing that. It's not having that interaction. It's dark. But it does have gravitational interaction. We know that because that's the point. It's doing stuff to these galaxies that we just can't explain in any other way.
Exactly. Yeah. So we can say it doesn't interact electromagnetically, which is with photons, but it does interact with gravity, and that turns out that you can actually bend photons with a bit of gravity, which is a useful technique to spot this dark matter as well. Right.
So the obvious question, Emily, is like you've had more than 50 years, and I'm looking at you directly now. I'm placing this responsibility directly on your shoulders as representative of the astronomical community. You've had more than 50 years to solve this problem. What are the best candidates so far? What do we think this stuff is?
Yeah, well, that's exactly kind of what the astronomers do. We draw up a list. These are all the possible ideas we can have, all the ways we can explain it. And we start off with, double checking our facts, double checking our measurements, double checking our theories. And every test that we've put our current theories through, every new observation that we make, it just doesn't change the answers that we're getting.
Right.
So we're kind of leaning away from those ideas.
It's not just the rotation curves of galaxies either, is it? That there's other reasons to think that dark matter is there. It's not just that your equations of galaxies are broken.
No, it's equations of physics. It's gravity. It's all the things that we think we understand, and there's just no way that we can even reorganize those pieces of physics to get a consistent answer with dark matter. So we think that the physics is still right, and we think that dark matter is therefore a real thing.
It's a real thing. It's just not clear exactly what it is. And it really does blow my mind that the best part of 70 years later, we're still fumbling over this question. I mean, I say fumbling, that sounds really bad. We're still really working hard at this question of what is this 85% of the universe. So, Emily, what are the leading ideas? What are the leading candidates?
So we've thrown out that our equations are wrong. We're confident that that's not the case. We now got to the point of, well, there could be these kind of large clumps of stuff that we just didn't know about before.
Like what sort of?
Could be like giant planets that we haven't seen before. Could be black holes, big black holes within the universe we haven't seen before. Anything and everything we thought of. And what we've done is we've gone and surveyed the galaxy. We've done immense, very, very precise observations. And we're now so confident that we've done these surveys very, very well that we know that there's nothing bigger than about half the mass of the Earth that could be dark matter. We're confident in that now.
Right. Okay. So that first idea is it's dark in the sense that we don't see it, but it's nothing special. It's the same stuff that we have around us. It's just not going around stars. It's not lit up like a star. It's floating in space as maybe planets or bits of stuff or loads more dust or whatever it is. But it's normal matter. It's stuff that we recognize. And is what you're saying that doesn't seem to be right? It's not that.
It's not that. We went and hunted for that and we didn't find it.
It's not there.
It's not there.
Yeah. Okay. So what else have we got then? If it's not stuff we recognize, it's something new?
Yeah. So we've got to go down the list of possibilities. And the next one on the list, which is the one that we're going to be looking at into tonight, is the best type of dark matter candidate we have is something called a WIMP.
A WIMP. Is that opposed? I remember reading about this. Is that opposed to WIMPs and MACHOs? Was the MACHO the previous one?
Yeah, MACHOs are the big things.
What does that stand for?
And the WIMPs are the little things.
The MACHO stands for?
Massive compact halo objects.
Right, okay, so that's the MACHOs. And then the WIMPs are?
Weakly interacting massive particles.
Okay, so tell me about WIMPs. How would a WIMP solve our problem tonight?
So WIMPs are one of our best candidates for dark matter because, so if you go through the name, it actually kind of leads you through what they are. So they're particles, if we start at the end. They've got some mass. That's great. That helps us with the mass problem.
Okay, good.
And they're weakly interacting. So they don't interact electromagnetically, or if they do, it's so subtle that we just can't detect it.
Right. Okay, but that's kind of cheating, isn't it? Because all you're really doing is just restating the problem. You've just said, dark matter. No. It's weakly interacting massive particles. Great. What are they? Have we found any of these? And I guess we'll get to that in a minute when we talk to our guests. But we've been talking about this for a while as a species, as a field of astronomy. Has there been any success to date?
There has. When we've discovered loads of particles. I mean, if there's one thing we are good at, it's finding particles.
Yes, it has been a good half a century for particles as well. It's true.
Yeah. And one example which you might have heard of before is the neutrino.
Right. Yeah.
So this is a very, very tiny particle, so tiny it barely has any mass at all. But there was even mass.
Yeah, there was a lot of consternation about, do they have mass? Do they not have mass? I don't know. It's so small, it's even so hard to detect. But that's for sure now? They definitely
they've got tiny, tiny, tiny mass.
Fantastic.
And neutrinos are everywhere. They're produced in the fusion reactions in the sun. They're produced in supernova. They're just all over the show.
There are ludicrous numbers passing through our bodies every second from the sun. I remember reading that.
Yeah, exactly. So neutrinos are neutral, so they don't interact kind of with normal atoms, which is why they kind of just pass through us. They pass through you and I, they pass through the Earth. They're just not interested, basically. Mm-hmm. So they were one of the ideas of these kind of WIMPs that were put forward and think, well, if you add up all the neutrinos, does that explain dark matter?
And so does it?
I know. There's just not enough of them.
Okay. So it could have been neutrinos. Neutrinos do have mass, but it's not neutrinos. It's something else. Okay, next.
Well, then we go to hunting for other particles that it could be. So there's lots of criteria. It's actually, we keep saying as astronomers we don't know anything about dark matter. We actually know quite a lot of what dark matter is and what it isn't in terms of the boundary conditions. We know it must have done particular things at the very beginning of the universe. We know it must do particular things now. So any candidate for dark matter that's put forward must do particular things because we've made the observations and we can see them.
Right. What you're saying is whatever we find or whatever we hypothesize, whatever we're looking for, it's got to fit with all the other observations we've got. And we do have a lot of them going right back to almost the Big Bang. We're very close to the Big Bang and we've got a lot of observations. And so it's all got to match up in the middle. Is that what you're saying?
Exactly, yeah.
Okay.
And this is what got me so excited when I found out that my colleagues here at York had not only looked into one of these candidate particles, but found some stuff that starts to put the jigsaw puzzle pieces in place. And that is just amazing.
That is pretty exciting. Well, now might be a really good time then to introduce our very special guests here tonight from the University of York. Please make very, very welcome. And I know we can't hear you applauding at home, but do it anyway for Dan Watts and Mikhail Bashkanov. Sorry, Mikhail. Stumbled over your name there, but I'm probably not the first. Thanks for joining us. This is very exciting. And it's exciting for both Emily and myself because Emily is the astronomer who's hunting professionally for dark matter and would really love to know what it is. And for me, because I'm a lapsed particle physicist, right? 20 years ago, I did a PhD on quarks and particle physics, and I haven't done it since. And so anything that involves the stuff that you're looking into called a hexaquark, I'm all over that. That is really, really exciting. So welcome to the show. First of all, let me ask you, what exactly is it that we're talking about here tonight? We've heard Emily talking about WIMPs, weakly interacting massive particles. We've ruled out the neutrino. It's not that. So clearly it must be something new. So what is it that the two of you reckon you've found?
Okay, well, maybe a new particle, which is, as you mentioned, the hexaquark. So you're probably familiar, of course, you have the atom and you have the nucleus, and within the nucleus you have the protons and neutrons that are made of 3 quarks. Yeah, and for a long time, most of the particles discovered were either made of 3 quarks, like the proton and the neutron, or made of 2 quarks, for example, particles like mesons. So Mikhail carried out some experiments before joining us in York, colliding protons and neutrons together, and found strong evidence for this particle that's actually made of 6 quarks, which is, very unusual. He actually came to join us at York to join in the program with using very intense beams of photons to look for these particles. We're again seeing very strong evidence that they exist.
Now, this is really, really interesting because, as we mentioned a minute ago, we've had 70, 80 years of this huge explosion in our understanding of the fundamental level of matter in the universe. And you were talking about quarks, the stuff that's around us, the protons and neutrons that make up the nucleus in all of the atoms around us are made up of quarks, 3 quarks each. And we found all sorts of different things, 50, 60, 70 years ago, made out of all sorts of different combinations of these things. But is this the first time that we found a combination of quarks other than 3s and 2s? Is this the first time that's come up?
It is maybe hard to say. We have hints before that we might see particles with 6 quarks, with 5 quarks, with 4 quarks. And actually, the most compelling evidence for the 4 quark states come from Large Hadron Collider, 2002.
Right.
For most of these particles, we are not actually sure how many quarks are inside. It is very hard to say if particle lives for 10 to minus 24 seconds to count how many of them are inside.
Yeah, now that's a really important point, isn't it? Because the thing that we're talking about here, it's called the D-star hexaquark. Have I got that right? Okay.
Yes, that's correct.
The D-star hexaquark lasts for a very, very short period of time in the laboratory, right? In the particle collisions. How long did you say?
10 to minus 24 seconds.
10 to the minus 24 seconds. That's 0.0000, lots of zeros.
Yes.
More zeros than you really can be bothered counting. Seconds. That's ridiculously small amount of time. So I've got a lot of questions about that. I'm going to shelve that for a second.
Okay.
Point is, how do you know that it's got 6 quarks in it? That's such a short period of time. How could you possibly know that?
Well, because we can measure how it decays. And if we count the number of quarks of the decaying particles, we sum them up together, exactly like Emily sums up galaxies, and we come out that there were 6 quarks in the very beginning.
Gotcha. So you can work backwards from what you get to figure out what you had, and it's 6 quarks, albeit for a very, very short period of time. So that's, from a particle physics point of view, that's really exciting, and that's the sort of thing that makes me sit up and take notice, and a lot of science nerds out there will be very excited about that. But what is it that makes the D-star interesting for the Emilys of the world, the astronomers of the world? Why would a D-star particle, which lasts for 10 to the minus 24 seconds, how on earth could that possibly be a candidate for dark matter?
I mean, one of the most important properties of this new particle is that it's what's called a boson, which means, every particle has some intrinsic spin. The protons and neutrons have a spin of a half, electrons have a spin of a half, and that means that in the quantum mechanics, they really hate to be in the same place. So everything around us is mainly empty space because the electrons stack up in the energy levels because they're fermions. If they weren't, they would all drop to the ground state and there'd be no chemistry, and everything would be a lot more compact.
Right. So what you're saying is that the stuff that all of the matter that we see around us, all the normal hard stuff of desks and people and so on, it's all made up of a type of particle called a fermion, which has a particular kind of physics. And protons and neutrons made of quarks, they're fermions. But this one, the D-star, it's not a fermion. It's doing different physics here. And why does that allow it? Why does that put it up as a candidate for dark matter? Where do you then make that step?
So the fact that it's a boson, these kind of particles have exactly the opposite behavior. They can't wait to get into the same place. They all want to get into the same state, jump in the air. So they can form what's called a condensate, where effectively the electrons in the atom couldn't drop to the bottom state, but these bosons can. So they can all drop into the lowest possible state and form what's called a Bose condensate or a Bose-Einstein condensate.
Right. So they like hanging out together. They like gathering.
Yeah, they're really
in a large mass.
Yeah.
That's great. But I'd like to bring you back to something your colleague said a minute ago, Dan. Yeah. Mikhail said these things last for 10 to the minus 24 of a second. And Emily, I could be wrong here, but I'm going to go out on a limb and say that the universe has been around for considerably longer than that. So we've got some ground to make up here, Dan. And
maybe I can say. So we have examples how this happen, and like neutrons.
Right.
Neutrons are living for like 11 minutes, if they are in free space. 10, maybe or 11. Yeah. But if you put them inside nuclei, they live for quite some time. So we know that we can take a brick of gold from Romans and there will be still the same brick of gold.
So if you put neutrons and protons together in the nucleus, that makes the neutrons much more stable, much more resistant to falling apart as they would do if they were just
So you get some binding energy which keep them together and prevent neutron from decaying.
Okay.
So the main thing which we are looking for is an extra attraction. And Bose-Einstein condensation is providing us with extra attraction because all of these particles try to jump together in one place. They try to be close together, and that's exactly the attraction we are looking for. And that's an attraction which prevents them from decaying within 10 to minus 24 seconds. They suddenly become stable.
And they can only do that if they have this special kind of physics, if we like to call it that way, the boson physics. Not the fermion kind, but the boson kind. That's the only kind of physics. They're the only kinds of particles which will allow them to form these sorts of condensates. Is that right,
Yes.
Dan?
Yeah, I mean, in sort of thinking about this, I mean, one of the most famous states of a nucleus, the Hoyle state, which is key for helium particles sticking together to form carbon in the sun. A lot of the modeling of this state, the properties of this state are fitted best if you assume that has some component which is a Bose condensate of alpha particles, which are also bosons as well.
We were talking about that a couple of podcasts ago, Emily, when we were talking about the what was the famous paper, the
B2FH.
The B2FH paper, yes, and Hoyle. We were talking about the Hoyle state there. Okay. Yeah. So we seem to be making some progress here. We have a particle, right? The D-star hexaquark, which is exciting in and of itself, but it can form, because of its special physics, it can form this condensate, this Bose-Einstein condensate, which means that it can clump together in ways, it can stick together, and it can be bound, if you like, in ways that other particles normally wouldn't, which means it might be more stable. It can stick around a hell of a lot longer than 10 to the minus 24 of a second. So that's great. So my last really big stumbling block on this one, because this is all sounding really good, I'm on your side, is, but we don't see a lot of them around. Like, you had to work really hard to make one of these. It's not like you can just sort of, there's one, and pick it up and have a look at it. We just don't find them. So how could it be that a ludicrously elusive particle suddenly solves this problem for 85% of the universe? I don't know. Dan, do you want to field that one?
Yeah, I mean, it's a speculative idea, but as we've seen, we're looking for new ideas for this thing. So everyone's drawn a blank up today. But in terms of whether it's a little bit, it's analogous to why does light go through a window or through a crystal of diamond, for example? So, clearly the light goes through and will encounter millions and billions of particles as it goes through. And we know that light will quite happily interact with each of these particles, the electrons, for example. This really strongly, it will see one, it will interact with it in some way. But if you, in things like diamond and glass, the electrons form something that is not a condensate, but it's kind of a little bit analogous in that you have two bands of energy levels. You have the valence band, where all the electrons being involved in the kind of structure are. And then you have a higher energy, you have this conduction band, which is like a wonderland of free quantum states that an electron could go into. But visible light doesn't have enough energy to promote those electrons up to there. So it passes through billions and billions of these electrons, and the whole thing is transparent. Whereas if you looked at glass with higher energy, say X-rays, where it has enough energy to do this, it's actually opaque. So whether you can actually see things visibly depends a lot on how the properties are contained within the material itself.
Sure, that makes sense. Okay.
And things like a superconductor as well, which is a little bit analogous to what we're talking about. So the electrons can form Cooper pairs, which are in the simple model of superconductivity, which is like pretend little bosons, and then they can drop into a superconducting state. And as they're passing through the gazillions of electrons that they could scatter off and encounter resistance, they don't have enough energy to go to one of these free quantum states, so they just pass through. So you can have currents going around a superconducting loop forever, which is weird.
Yeah, okay. So it definitely is. Quantum. It's sort of quantum writ large, isn't it? Where when you get into those kinds of phenomena where stuff which we would normally expect to happen, like electrical resistance, for example, just doesn't apply in this particular case because it's in this special quantum state. And so is what you're saying that this particular kind of particle in this particular condensate state, look, it's just going to have properties which kind of line up with the sort of thing that we expect we would see from dark matter. It's going to be dark.
Yeah.
It's going to be dark for lower energy particles, but it may be not so dark for very high energy cosmic rays.
Right.
Because the energy of cosmic ray is enough to break it. And that's why we might see effects of cosmic ray breaking near condensate, or in other words, interacting with dark matter. But for this, you need very high energy cosmic rays, and that's exactly the way how we are going to detect these mysterious particles. So like looking from a glass, we should not see using light, but X-rays. Here we should use cosmic rays.
So what you're suggesting there is that there may be a few experimental, observational things that we can look for, ideas that we can look for to say, hang on, we didn't expect to see that, and we do, and it's kind of the signature that we might be looking for. Emily, I'm going to throw to you at this point. You've been sitting there very quietly as the astronomer. I don't know. Are you convinced? Is this solving all your problems? Are you doing a little excited astronomer jig over there, or are you raising a skeptical eyebrow? What do you think?
I am quietly excited, and I'm especially excited to hear that we can do more observational tests, because there's nothing more exciting than being able to go and get out my telescope again and say, well, okay, let's put this to the test. So what Mikhail was saying about cosmic rays is really exciting, because it turns out that cosmic rays are ubiquitous throughout the universe, right? These are not rare things. Cosmic rays are extraordinarily high energy objects or particles, and also photons you can get, which come from ultra high energy environments, but environments that we do understand and can observe. So things like supernovae reactions, or the centers of galaxies that are undergoing insane jets that we've talked about, I think, several times. So these cosmic rays are out there. I mean, I would normally, as an astronomer, say they're a pain in the neck. Actually, there's something that I try and get rid of, because I don't. If you've ever seen, if you take very, very long exposures in photography on CCD cameras, cosmic rays are things that light up your CCDs and cause streaks through your images where you don't actually want them. So in my actual research, I spend about 50% of my time trying to get rid of these cosmic rays. But now I can just hand them over to you guys and say, sort it out.
It's a win-win. That works. That's good. Yeah. One thing that I'm still really curious about, though, is, and I sort of alluded to it before, and I don't know which of the three of you is going to be able to answer this one. So I'm just going to throw it out to you and let you fight it out amongst yourselves. Where did they come from? Like, as I said before, we have to work hard to make one of these things. We've got to bash stuff together really, really hard and look really carefully to find them. But 85% of the universe, of the stuff in the universe, has to be accounted for. And so if it's going to be accounted for by D-star hexaquarks, there's got to be a lot of them out there. Where'd they come from? Who wants to field that one? Emily, Mikhail, Dan, anyone?
I can try.
All right,
if you allow me.
Come on.
So let's go back in time to very, very beginning of the universe. So we have a big spot of quark soup. Mm-hmm. There's a lot of quarks moving around. So there are no protons, no neutrons. Their temperature is too high for them to form.
So we're way back. Like this is before atoms. This is before any of this stuff.
Yeah, far before.
Yeah. How long after the Big Bang are we talking? Really, like
fraction of a second.
Fraction of a second. Okay. So boom, and then we're there. Quark soup. Good.
Quark soup. All just quarks. They cannot see neighboring quarks because there are too many of them and the interaction is screened. Okay. So that's one of the reasons why protons can be formed. Now, the soup is expanding and it's cooling down. And at some point, their quarks start to see each other, so they can form protons or neutrons or hexaquarks or hexaquark condensate. Now, since hexaquark condensate is a lot more bound, it is more preferable for quarks to make a condensate rather than make a proton. And one can calculate what is the difference in energy benefits you get, and from these energy benefits you can say how many hexaquarks should be formed and how many protons. And if you plug in all the numbers, it works out quite well. So you get your 85% of dark matter and only like 15% of normal matter.
Okay, so have I got this right? The picture that you're painting is this quark soup, and the very properties that you're discovering, you're hypothesizing about this D star, is that it actually really likes to form these clusters. I mean, it likes to form protons and neutrons as well, but it actually really likes to form this condensate. And in the very conditions at the beginning of the universe, where there's loads of energy, quarks swimming around, you're saying it could have actually just made loads of this stuff. But then the universe cooled, to a point where that wasn't energetically viable before, and that's it. We've got the hexaquark condensate, and that's out there, and we've got the protons and neutrons, and then that's it, and that's what we've got now. And we've just never noticed all of those hexaquarks before. Is that right?
Well, Emily noticed it.
Fair point.
This is amazing. I was going to let you guys off the hook, and I was going to say, you don't have to explain all of the 85%. I'm happy to take several WIMPs as the solution to dark matter. But if you can do all of it,
they're putting it on the table and saying, "We've got it. We have nailed the 85%."
Wow, it's a speculative idea that's new, and I think it's it's in the early stages, but it's we find it very interesting.
So Dan, are you being the voice of reason here and saying, "No, hang on, we're not actually"?
I'm not often that, but maybe I am.
Save the Nobel Prize for later. We'll worry about that another time. But I mean, that is a really interesting point, right? Because it is such a big question. It's one of the biggest questions in astronomy, surely. I mean, would that be right, Emily? That this is one of the big remaining questions. Is we've got to nail this one down, right? It's such a big question that coming up with the answer would be very, very compelling. So, can I ask the two of you, and maybe Dan, I'll go to you first. How speculative is this? How confident are you? Is this the answer? Is this an answer? Is it a fun idea? Where on that spectrum are we?
It's a very new idea, which from the preliminary calculations that we did seemed to come out very surprisingly plausible. And so that was kind of the stage we're at. I mean, the paper was to provoke more detailed calculations, but also, I mean, one of the key things is that if these things do exist, okay, there's a lot of questions. I mean, strongly interacting condensates is, a very new field, and, there's a lot to be learned on that in more detailed theory. But because we know if this thing gets broken, we know exactly how it will decay. We know the energies of the gammas it will emit. We know it will emit deuterons. We know the pions because the decays of this particle have been studied so well. So if the condensate gets broken, you will get a massive flash of gamma rays with a certain characteristic energy spectrum. And so one of the things we're really keen for was to actually put that out so that astronomers could actually look for these kind of signatures. And there's been some follow-up papers where astronomers already tried to kind of look at the gamma ray spectra using these kind of hexaquark models, which could rule in or rule out this new possibility.
I was going to ask that. Is it, are there observational runs going on now? Has there been some interest garnered out of this one for people to start looking back through old data or collecting new data to say, hang on, is this there? Can we see this?
Yeah, that's all going on. Yeah, so there's been, there's at least a few papers coming out with that, trying to constrain the contribution of hexaquarks to dark matter from the initial observations. And there's recent work that Emily will probably know about how the location of dark matter in the universe seems to have some correlation with gamma emission. There's quite recent paper on that. So things are moving, but as you talked about in the start, it's exciting and unknown physics.
Yeah, and I can add, the bar is like here, right? It's not kind of like you come up with a new idea for dark matter and you just pump it out in the next journal paper and you move on and do something else with your research, right? When you are answering one of, as you say, the biggest questions, and I would argue not just astronomy but in all science, there is a level of kind of carefulness and a level of proof which you've got to get to before you can get to an acceptance. And by no means, I think Dan and Mikhail are saying that we're there yet, but they're saying, hey, we've got this idea, it's consistent with some of the characteristics we know dark matter to have, and let's test more and see how far we can run with this.
Goodness me, very, very exciting times on the particle physics side and on the astronomy side. Emily, I don't know. There have been, I sort of feel like there have been a whole bunch of different, peaks of excitement and moves in a particular direction about dark matter. I remember talking to a particle theorist a couple of years ago about, raking through all of the data that's come out of the Large Hadron Collider for new physics, for supersymmetric particles and all sorts of other nonsense like that. There are so many ideas out there. What's your feeling, Emily, on is this the right area to be looking in? Should we be focusing on other things as well? Is it a matter of looking in every possible direction that we can go? What's your view on how we should be approaching dark matter at this point?
That's a very big question, but I think we have to acknowledge the progress that we've made in this field. When we started out, we wrote down our list of, well, it could be different theories of gravity, it could be these MACHOs, it could be these WIMPs, it could be this, and this. We've gone a long way into a lot of these investigations. We've reached the point where we've ruled out so many modified theories of gravity, for example, that just don't fit the observations. So we move on. We've ruled out so many types of MACHOs, these big objects like, just extra bits of stuff left over from galaxies and things like that. We've ruled out those. We've ruled out lots of other particles as well, like the neutrino. So it is a process of elimination, but all of those processes are done at the same time with which we get more observations and we get more understanding. We've got now things like the first light from the universe. So this is called the cosmic microwave background. So we have lots of information about what dark matter should do to influence that piece of light from the very, very early universe. And that gets folded into the set of criteria. And then we've got things like, we've now been able to measure things like the abundance of lithium in the universe. So we have constraints on what dark matter can do or not do to change that number. And every time we do these things, we're narrowing down the sets of possibilities, I think, for what we can do. And sure, there's lots of extreme theories out there, and if you've got a really favorite dark matter candidate theory, I don't want to be too dismissive. But the general consensus amongst physicists and astronomers is that we're moving into this particle physics solution broadly, and something like, if it's not exactly this particle, something like it seems to be the top probabilistic playing card, if you like.
It's exciting. It's exciting stuff. I find as we're getting to the point in this particular episode where we're going to need to turn to some of the audience questions. I think we've over the last 45 minutes or so, we've covered a lot of territory. We've looked at one of the biggest questions that we have in astronomy, one of the biggest unanswered questions in science, I think. We've gone down a bit of a particle physics rabbit hole there, but uncovered a whole new kind of particle that we didn't even know was there before. There were hints, but now we've got some really good evidence for it. And not only that, but this particle potentially helps us to solve a problem on the other end of the distance scale. We're going from tiny fundamental things of a minute fraction of a centimeter and a tiny period of time to the length and breadth and history of the universe. This is a big story, and it's been really so much fun to have you on the show, Dan and Mikhail. Thank you so much. Will you stick around to answer a few questions for the next 10 minutes or so? Got a bit of time?
Definitely.
Fantastic. All right, Dan, I should just warn you, you're on mute there. So if you want to answer a question, let's go to some of the questions from the audience. We've had a whole pile of them. So I'll just sift through a few of them. The first one that I'm going to come to is, maybe we should have addressed this one up front, Emily, is the difference between dark matter and dark energy. There's a couple of questions in the Q&A chat here asking, hang on, does the 85% that we're talking about, does that include the dark energy? Does this particle account for dark energy? So Emily, could you give us just a quick primer on what's dark energy first, and then maybe Dan and Mikhail, you could answer as to whether or not that's part of this question. So Emily, over to you first.
Yeah, dark energy is another really embarrassing part of astronomy. In fact, so if we've been talking about matter, so this is mass, stuff that has mass, stuff that interacts via gravity, right? Now, it turns out that matter only makes up something like 30% of all the energy budget in our entire universe. So that's the dark matter and the ordinary matter that we understand. So if we took the energy budget of the entire universe, we've got 5% the stuff we know, 25% dark matter, and then there's a 70% of dark energy. And yeah, that's really...
So we thought dark matter was embarrassing. Dark energy is even more embarrassing. Okay, so I mean that does sound like a podcast for a whole other time. But Mikhail and Dan, is what we're talking about here with the D-star hexaquark, does that have any impact on the whole question of dark energy at all, or is that a whole other topic?
Yeah, I mean,
no, so it's it's just matter. So the question for dark energy should be addressed to other people.
let's just solve one problem.
Yeah, one problem at a time.
I was really hoping you had something for that, and maybe on inflation in the universe. Can you help us out?
All right.
This other thing that
I need to look up in my papers.
Okay, so it's not the dark energy. It's just the dark matter. But it's an interesting problem. Maybe we'll just have to dig a bit deeper on the dark energy next time. But on to the next question, which is there's been a couple on this one as well, which is there have been plenty of other searches for dark matter. I mean, there's been one actually not terribly far away from here in the is it pronounced Bolby potash mine near Staithes. There was a big underground experiment in the Italian mountains and so on, looking for dark matter. Like, are those still going on? Those experiments which are looking for signs of whatever the hell these particles are those experiments still running, or is that era been and gone? Emily, maybe we start with you on that one.
Yeah, absolutely. So the kind of experiments that Dan and Mikhail are involved in and been talking about is something like the particle colliders, where you're smashing stuff together at high energy and you're creating the particles for you to study. The kinds of experiments that are running, for example, at Bolby Mine, are looking at particles coming from the universe just naturally, if you like, and trying to understand those. So we're interested, neutrinos, for example, are one of the things that we do try to detect with these kind of instruments. Now, it's very, very hard to detect something that doesn't want to interact. It's almost like it's against you at this point, right? So neutrinos are a great example of things that are really hard to detect. And anything that's going to be weakly interacting is going to be like that. I was gonna say this to the end, but I'll tell you now, because I think this is if you're going to take away one fact about dark matter, it's obviously the D-star hexaquark. Is your other fact that you can take away with you. To give you an idea of what a needle in a haystack this is, if we added up what we anticipate to be all the dark matter that's in the volume of the Earth, then you get something like the mass of a squirrel.
That's a lovely mental image. I love it. A dark matter squirrel. I mean, that does relate to one of the other questions, which is in the list here, which is, if there's all this stuff out there, is there any chance of a rocket bumping into dark matter in space? And I've now got a mental image of the SpaceX rocket going up and just bashing into a dark matter squirrel on its way. But I'm gathering from what you're saying, Emily, that's very unlikely. It's incredibly spread out. Would that be right?
That's right, yeah. So you take your squirrel and you've got to spread it out over the entire volume of the Earth.
This is going places we don't need it to go. All right, next question for Mikhail and Dan. I might throw this one to you, Mikhail. How do you measure? I keep coming back to this. 10 to the minus 24 seconds is a ludicrously short period of time. I think we'd all agree on that. So how on earth do you make measurements on something that lasts for that shorter period of time? And I realize the answer to that will be, it's technical, but if you can in, a very short period of time, like a minute, how do you measure things that last for that short period of time? That's crazy.
Well, you might heard about uncertainty principle. This tells you, if you measure some distances with certain accuracy, you cannot measure momentum with similar accuracy. Now, that means that if your particle lives for a very short time, the accuracy of your energy is predetermined, more or less. So if you construct the momentum of all your particles, which you measure from the decay, and you try to reconstruct the mass, you don't have one mass, you have a spread. Even if you measure all of your momentum and direction of your particles perfectly. And the spread in mass, due to this uncertainty principle, more or less, exactly gives you a lifetime. So in this sense, the shorter your particle live, the better, because then the more clearer you see the spread.
Right.
Well, if your particle is long-lived, it's just a needle.
So what you're saying, if I'm understanding you correctly, is you're not actually getting in there and going, okay, there, that one there, that one there. You're not measuring 10 to the minus 24 of a second. You're not starting your stopwatch and finishing it at 10 to the minus 24 of a second later. You're inferring that time frame from huge amounts of data that you're picking up on presumably very many of these interactions, these decays of the D star. You're collecting lots and lots and lots and lots and lots of data and working backwards to say, well, that thing that's giving us all of these decays, it had to have lasted for this period of time. Is that right? That the maths is telling you that. Basically.
So let's say you have D star decays into, let's say, 4 particles. You sum their energy, you get one number. You sum it again, you get another number. Third, second, millions of times. And then their most probable number gives you its mass. And the distribution of these masses gives its lifetime.
Gotcha. Okay. I'm glad to hear that, because the whole 10 to the minus 24 was really beginning to break my brain. Dan, I'm going to throw this one to you, because perhaps you could explain where this D star hexaquark fits into our particle zoo. The question that came up was, so do we need to add the D star hexaquark to the standard model? Is this something that we need to sort of expand out our understanding? So maybe, first of all, what is the standard model?
Well, so the standard model is the sort of the basic, as we envisage them at the moment, fundamental particles from which everything around us and in the universe is made. So a key grouping in the standard model are particles called quarks, which interact via the strong force. So you have kind of light quarks, which are called up and down, and then you can go up to strange, charm, bottom, top. So there's a whole family of different quarks. And this D-star particle is made from the same quarks as what the proton and neutron are made from, the up and down quarks, so the very lightest quarks.
Right. So we're not expanding the standard model as such. We're sort of expanding the repertoire of things we can make with it.
Yeah. Exactly. Yeah.
Right. Right. So the D-star hexaquark is kind of like a weird cousin of the proton and neutron.
It is, yeah.
Yeah. But one that we really haven't seen before.
Very, very.
You know, you sort of open the door at the family party. Oh no, don't.
Yeah.
He's a weird one. Fantastic. Having a quick look. We've probably got time for maybe one more question. So while I'm digging through, Emily, do you have any questions that you want to throw at Dan and Mikhail?
Well, my original one was that, can you solve all my other problems?
Look, I think you've actually done pretty well tonight, actually, Emily. I'd just keep quiet if I were you. I think we might finish on this one, which is, could you talk a little bit more? And I guess, Emily, you might be able to talk to this one, but I think Mikhail and Dan as well. The question is, what sort of telescopes, detectors, and observations would you need to find or eliminate the D-star hexaquark? And I think you talked before about, as you say, the interactions with potentially very high energy light photons. You might see a signal there. But can you talk any more to that? What sort of observations would you really like to see happening next in order to try to nail this one down?
Well, you guys tell me what good you need, and I'll tell you how to do it.
It'll be the start of a beautiful collaboration.
Well, there are plenty of detectors already running.
Yep.
So since right now we know what should be the signatures of this dark matter, we can look up in already collected data. And detectors like Fermi-Large telescope, which is flying in space and looking for high-energy particles, is very well suited to it. So we would like to have a better directional resolution from the same telescopes, and that's probably in years to come. Or let's say we can use moon as a shield against all of our cosmic rays and look for high energy photon splashes with high multiplicity, which is coming out from the moon. So that's one of the possibilities. And then if you place your detector close to a moon, you're very well shielded from everything else, and you can see the dark matter break up by flying by cosmic rays. So things like that might be a good idea.
I do love the way someone can just casually say, and if you just use the moon as a shield, like if that doesn't get you points at your next cocktail party, I don't know what. Dan, over to you. What's your response?
Yeah, just to add, it is a very unusual particle, and one of its unusual properties is it very much likes to decay to a deuteron. So when these condensates break, it might well be that there's a kind of associated with a kind of a deuterium excess, which is kind of quite a rare sort of nucleus in the universe, and that might be another indirect signature of the role of this D-star if deuterium correlates with dark matter.
Okay.
So Emily can do that next week.
All right.
Hang on, I already signed up for the moon mission.
Well, we got at least several funding applications to get in fairly quickly, Emily, on that one. Listen, we are going to have to wrap this one up. Unfortunately, we are out of time. I would like to just express my thanks, along with the thanks of a whole bunch of people who are throwing their thanks through on the Q&A here, to Dan and Mikhail. Thank you so much for joining us on this episode of the Syzygy podcast. It's been great fun talking to you. Look, I really hope you're right. On the other hand, it's always really nice when science kind of goes, that's a great idea, but here are some issues. Let's debate this again for another, 50 years or something. So I really look forward to finding out what happens from here. Thank you once again for joining us on the show. Thank you to everyone who's been listening at home and joining us for this very special event. We don't normally do these live broadcasts, so it's been great fun to do it. And thank you to everyone at the York Festival of Ideas for making this happen. I should point out, we have been recording this, so if you want to go back and watch it again, or if you only just managed to join us for the very end and you're really confused at this point, go and watch it again from the very beginning. Just go to yorkfestivalofideas.com for all the details. And you can go there as well to find out the details of what else is happening in the rest of the festival over this coming weekend. There's still a bunch of stuff happening tomorrow and on Sunday. So go to yorkfestivalofideas.com for all of those details. Another website that you really should check out is syzygy.fm, which is a home of our podcast. We're also all over the social medias. We're on Twitter and on Facebook and Instagram and all of those as well.
Absolutely.
So,
and if you had a question, I saw there were some amazing questions that we just unfortunately didn't get time to look at today.
To everyone,
so if you do have some of those, they've got a contact form on our syzygy.fm website, so you can trot along there and contact us that way as well.
Yeah. I'm really sorry we couldn't get to all of the questions, but we do have a finite amount of time in the history of the universe. Look, we'll be back again with another episode of the Syzygy podcast in, as we always say, roughly a week or two. We'll see how things go. In the meantime, thank you for joining us. Thank you, Mikhail and Dan, once again. And we'll catch you all next time. Emily, see you later. Thank you very much for joining us on the Zoom. Good night, everybody. Thank you very much.
Good night.